Greetings everyone. Welcome to the second chapter of set theory. We defined sets in the previous chapter. We looked at the naive definition and we looked at equality of two sets when two sets are called equal. And today we are interested in seeing how do sets interact with each other. That is, what are the ways of operating, so operations on sets. What are the ways you can combine two or more sets, operations on sets, or I'll write algebra of sets. Algebra of some structure in mathematics means the operations that can be done with that structure. So algebra of sets. And we know of a few operations already: plus, minus, divided by, and multiplication. These are algebraic operations on real numbers, but we have defined a set in a very unique way. It's just a collection of well-defined objects. So just with that very general definition, collection of any well-defined objects. So maybe I have two sets 1, 2 and 3, and I have another set 0 and 1. I am interested in knowing what all I can do with these two sets. So let me name these two sets. I'll call this A and B, and let us first try to so these both are collection of elements. Let us try to form a set which contain all the elements from both the sets. So as simple as it sounded, it's just a collection of all elements from all the sets. So how do you write it? I'll write it in ascending order. You don't need, okay, I'll not write it in ascending order today. So I'll write 1, 2 and 3 first. I have collected elements from A. What's left from B? There's 0 and 1. 1 we have already written, and you don't repeat elements in a set. We saw that it's just a collection, so there's no sense in repeating. It's just a collection of something. So I'll just write one more 0 here, and I'll not write this one. It's understood, it's already there. So this we called the operation of union. Union is one or more people coming together, right? So A union B, I'll write in black color, A union B. This is the symbol for union. A union B. So this is called the union. How do you properly define what a union is? A union B is the set such that set of all elements, say X, such that X belongs to A or X belongs to B. So now you should know the meaning of this statement I just made. I'll write the whole statement. The set of all x's where X belong to A or X belong to B is union of A union. So is A union B. So this is the proper definition written in mathematical language. If this language is confusing to you, these symbols are confusing to you, and this OR is very confusing to you, you should just repeatedly watch this again and again, and you should watch also my mathematical reasonings videos where I covered all this formal mathematical jargon in a playlist, which we will keep on using again and again. Okay, so that's the union of two sets. Any other example would be the union of two sets N and Z. So what is N? N is the set of all natural numbers. Z is the set of all integers, Zol, if you remember. So union will be, so what is the set of all integers as well as natural numbers? So we know that N is a subset of Z, right? So the union will essentially contain only the elements from Z because it already contains all the elements from N. So since n is the subset of Z, the union is just Z. Then we have something called, so now we saw that this thing gives us an idea of what else we can define. This OR gives us an idea of what could have gone the other way. The set of all x's such that x belongs to A or x belongs to B is one way of combining elements from A and B. What can be another way? The set of all x's, I'll write it in this color here, the set of all x's such that x belongs to A and x belongs to B. So how will this look like? What will this look like for these two sets? So all such elements which are contained in both A and B should be in my new set, and I'll call this set the intersection. The intersection. Intersection. A intersection B would be just the element 1. It will be a singleton if you want to be fancy. Singleton set 1 if these sets are given this way, because 1 is the only common element we have. So this is intersection. What is happening? I'm pressing the undo button. Yeah. And this was union. And we saw two ways of combining elements, right? And let me show you one more example of intersection, one more interesting example. I'll show that example now. So I have say that I have a set of all rational numbers. Remember, rational numbers or Q are quotients or ratios of numbers. That is, all the numbers of the form m by n. All fractions or all numbers that can be represented as fractions come under rational numbers, where m and n are integers. So these are all the rational numbers, and they are denoted by Q. So numbers like 1 by 2, 2 by 3, 4 by 49, or all such numbers will come under Q. Intersection, I want to intersect this set with all square roots of primes. Well, first of all, think about it. Pause the video, think about it here, and hoping you thought about it already. So all square roots of primes, is this a set? First of all, we have to check that. So is it well defined? Well, why not? Because if I give you some random number x, you can tell me whether it's square root of prime or not. So if x is something like root 7 or root 23 or root 11, you will say that x belongs to this set. If not, then x does not belong to this set. So you can explicitly state whether x belongs to this set or not for any given x, right? So all square root of primes is a well-defined set. It's a set. How will the set look like? Well, what will the first element be? What will be the smallest element in the set? We don't need to have a smallest element in all sets, but in this case we will have one. So I'll write this green set, I'll write here. This set I'll write here. This set will be something like this. So what's the first prime number? First prime number is 2. So I take the square root of it and I put it in the set. And the next prime number is 3. I take the square root of it, I put it in the set. So root 5 will be there, root 7 will be there, so root 11 will be the next number, root 13 will be there, and so on. But if you see, none of the numbers given here can be rational. and we have done this proving multiple times, right, in our previous classes. Root 2 is not a rational number. We have proved it using the proof by contradiction method, if I'm right. So proving by contradiction method, you prove that root 2 is not a rational number, root 3 is not a rational number, and you do this for general root p is not a rational number where p is prime. So this green set essentially contains all irrational numbers. Not all, but whatever is contained in the green set is an irrational number. So all numbers are irrational in this set. So can an irrational number be represented as a rational number? No, they are disjoint subsets. So I just use the term disjoint. In fact, I'll let you know what disjoint is in a couple of seconds, but they are not joint in any way. They don't have any elements in common. So what does Q intersection this green set leads us? So it's nothing. It's empty. So this is the reason why we need the notion of nothing in sets. Notion of nothing. I didn't define it in the previous lecture because I didn't want to give it as a definition. So it comes out of necessity, right? We have sets like these and we have intersections to perform on them, and hence we have something called nothing in the case of sets, and it's denoted by this empty brackets, or it's often denoted by this Greek letter phi, small phi, and it's called the null set or empty set or nothing, whatever you want to call it. But this thing Q intersection, my fancy set I just gave you, I'll just call it K for now. So this set will be equal to nothing. It will be equal to phi, or it will be equal to this symbol. This is to say that they are disjoint. They are not joint in any way. There are no elements in common. They are disjoint. Not they, these two guys. These two guys are disjoint. And this is called the null set. I don't want to bombard you with all these terminologies, but we'll keep on using these. You don't need to remember these as usual. That's one more example for intersection. Now we saw ways of combining two sets. So this addition I think is fairly taken care of for now. We saw two ways of combining sets. So I'll rub off this addition symbol. Now we have left this so we'll take subtraction next maybe. So how do you subtract two sets? So say that my A is same as before, 1 2 3. B is the same, B is 0 and 1, the same set. And do remember that we are defining these operations. No one has told us that union should have been this way. There could be some other way you could have combined these two sets, and I encourage you to think of such ways, but it's a convention that union is this way of combining, and we assign it a symbol, we define the union. So you should understand the difference between a definition and just a mathematical fact. A minus B, sometimes it's called A difference B, or you can write it this way just to differentiate it from the usual difference operator, usual minus. We write a slanting, this is a forward slash I think, to denote the A difference B symbol, and this I am defining it as the elements. In this case, in fact, I'll like to represent this as a Venn diagram first, which will be more intuitive to you. So we saw that A could have been represented as a circle in the previous lecture. So there are sets, you represent them as circles, and you represent the universal set, maybe it's the set of natural numbers, universal set as the rectangle, and B will contain the elements 0 and 1, A will contain 1, 2 and 3, 1 will be in the common area. So all these are the benefits of just constructing them as a circle. You'll be able to look at where the set overlaps. A difference B is geometrically, if you just think about it, you just take away B from A. So take away all of B from A. Whatever you're left with, we call it A difference B. So essentially it is 2, 3. How do you define it formally? All elements, or I'll write it in X form. We had all X's such that X belongs to A, but so I'll write and X does not belong to B. These both things should happen at the same time. That's why I have used an AND operator. So X belongs to A and X does not belong to B. One doesn't satisfy that criteria. One belongs to B as well. So this statement is false, and hence we don't take 1 into our difference set. 0 is anyway not in A, so we don't talk about that. 2 and 3 satisfy these criteria, and hence the only elements contained in A difference B would be 2 and 3. We'll have one more example of difference in the later part of the same lecture. So for now, I'll also show you quickly what the Venn diagrams for these two guys are, intersection and union. So how will the Venn diagram look like? This you should do by yourself. I encourage you to do by yourself. You can cross check with me again. So if this is A and this is B, A union B would be something like this. Elements in all A and B. Whatever elements we have in both, we write everything there. And this is of course the universal set. U can be anything here. It can be natural numbers, integers, or real numbers. I'll just write U for now. And intersection, Venn diagram for intersection would be, this is the Venn diagram for union. I hope I said it. I didn't miss it out. This is the intersection Venn diagram for union. So Venn diagram for intersection would be something like this. All the common elements. Right? Looking at Venn diagrams is much easier a lot of times because geometrically you can understand things. Especially in this case, it was helpful. So we took care of difference. There's something else I'd like to introduce along with difference. Now that we are already talking about Venn diagrams, there's one more thing you can do with sets. Say that I have a single set A, and A has a few elements. Say I don't know what the elements are. I'll just draw dots, and there are a lot of elements outside in the universe. So universal set has a lot of elements. A complement, I define it to be this shaded region. So I am giving you various ways of defining things. This is a completely geometrical way of defining. So what is the mathematical way of writing? I'll call it A dash or A complement. This is called complement. So A complement is something I am defining to be all x's where x belongs to A. So or all x's where x is some element such that x does not belong to A. I'm sorry if I said x belongs to A. So all x's such that x does not belong to A. So if you give me some element, say it might be easier if I do it with numbers. I am complicating this because I didn't want to give you an example here, but anyway, 5, 8, 9, 10, 11, 1. So here if I give you any x, say 8, if it belongs to A, this 8 belongs to A, then I'll not put it in A complement. if I give you 9, then I'll put it in A complement, because 9 does not belong to A. 9 is outside somewhere, outside of A. So A complement in this case, in my specific example, would be 11, 1, 10, 9 and 2. Assuming all the elements in the universe are just these elements, there are no other elements. So this is something called the complement of sets. Complement. And we have, I think, exhausted our minus symbol also here. So minus is done with. Division on sets. You can define division on sets, but we don't need that for now, because things might get complicated, because all the sets need not be integers, right? We have defined division on integers. So our union and intersection depended on the sets being the collection of just elements, but you cannot divide two elements. There's no such thing as dividing A by B, where A and B are just two alphabets. So division, we leave it for now. There might be several definitions in some specific cases, but we'll talk about multiplication for now. Multiplication, this 2 we are defining to be some special operation. A is 1, 2, 3 as before, and B is 0, 1. So how do I define multiplication on these two sets? I'll write each of the terms. So this will be a big set in which I'll have ordered pairs as my elements, and I'll have a few ordered pairs. We'll see how many shortly, but an ordered pair is where the order matters in a pair. It's a two element bracket form. So this will be of the form A comma B. It's a two element bracket, and the order matters. So this is called an ordered pair. And to define the product, A cross B, I am calling it cross, you can call it whatever you want. A cross B is the first element taken from A and the second element taken from B, and all such possible combinations. So 1, 0 will be one such combo. 1, 1 will be another such combo, and mind that 1, 1 is different from 1, 0, because at least one element differs. So sorry, 1, 1. And then we'll have 2, 0 and 2, 1. We'll have 3, 0 and 3, 1. So now you'll know exactly how many elements we'll have in A cross B, because A has 3 elements and B has 2 elements. For each of A's elements, there exist as many ordered pairs as there are number of elements in B. So for 1 there will be 2 ordered pair, for 2 there will be 2 ordered pairs, for 3 there will be 3 ordered pairs. So for 3 also there will be 2 ordered pairs. For 1, for 2 and for 3, both will have 2 ordered pairs each. So these are ordered pairs for 1, these are ordered pairs for 2, these are ordered pairs for 3. So total number of ordered pairs would be number of elements in A, number of elements in A times the number of elements in B. And this is also very alike to our normal multiplication, right? This multiplication is our usual multiplication in real numbers or integers. So this is how we define A cross B. If you are new to the ordered pairs argument, or if you are looking at ordered pairs for the first time, don't worry, there's plenty coming in relations and functions, because That chapter will be all about these ordered pairs, so we'll go in detail there. Now you just need to know that this is also a way of combining A and B by multiplying. We call it multiplying, but we just arrange it in an ordered pair. So with that out of the way, I'll give you two more examples quickly and we'll finish off the lecture. These examples would be interesting, so I just attached it to the end of the lecture. So the first example 1, I want you to find the union of Q and this set R minus Q. So people who have watched my previous chapter are aware that I said this is the symbol for irrational numbers, and I'll give you the reason in the next lecture why this is the symbol for irrational numbers. I just asked you to look at it as a single symbol there, but now you know R minus Q, R difference Q, is actually all the irrational numbers we have. This is nothing but the set difference we introduced there. So I think I introduced the difference right here. Yeah, it's there. So this is the set difference. So we have a lot of rational numbers in our number line. So we have a lot of rational numbers in the real number line. We subtract all the rational numbers. Whatever is left, we call it the irrational numbers. Because they are not rational, they cannot be expressed as a fraction. So real numbers minus all the rational numbers would give us irrational numbers. But I am interested now in the union of these two sets. So what is the union of, hoping you have paused and tried already. What is the union of rational numbers and irrational numbers? So it's just R, right? All real numbers. All real numbers. So now you also know what's the symbol for irrational numbers. This is often used in mathematics. So I'll just stop with one more example. Example 2. And just understand 75% of the example I'm going to give you, because we will discuss this later anyway, but just concentrate and listen to it. Even if you understand 75%, I'll be very happy. I'll be content. And so the example is A is some set. I am telling you what A is. So A is all real numbers x such that 0 is less than equal to x is less than equal to 2. And B is some other set of all real numbers x such that 1 is less than x is less than 4. I want you to find A minus B. A minus B. So let me approach the problem geometrically. We'll try to understand, because as soon as we see real numbers and this inequality, it helps me to draw a real number line. I'll mark 0 and I'll mark 2. What is my set A? Well, it says that all the real numbers, these, what is this condition? We can write it in a different form like this. You can write it as x is less than equal to 0 is less than equal to x and x is less than equal to 2, right? This is actually written as 0 less than equal to x less than equal to 2. So this is the actual condition. So what does this mean? All the numbers between 0 and 2, but you also include 2 and 0, because x could have been equal to 2 and 0. So I'll mark it this way. This is just a notation. This is just a way of marking stuff on real number line. So I'll put a circle and I'll shade it in, suggesting that 0 is included. I'll put a circle, I'll shade it in, suggesting that 2 is included, and the whole other set of numbers in between are included. So I'll depict it with a straight line. So this is graphically, you can call it this set A. So I'll write the set name here. This is set A. And what is B? I'll write it in the same number line if possible. So what is B? So 4 would be somewhere here and 1 is somewhere here. So B is all numbers between 1 and 4, but you exclude 1 and you exclude 4. So B is I'll choose this pink color for B. So B is, you exclude 1, so you just draw an empty circle. You exclude 4, but you do include all the numbers in between 1 and 4. So now you have two sets. Graphically you know what the sets are. Now you just have to find A difference B. So what is A difference B? All the elements that are in A but not in B. Remember what was A difference B? A difference B was this, all the elements in A but not in B. So whatever is in B, I'll subtract it from A. So all these things starting from 2 is there in B, so I'll subtract 2 from B. Whatever I'm subtracting, I'm coloring in with my yellow, or I'll use this eraser, that will be better. So whatever is in B, so this is in B, so I'll erase this. This is in B, so I'll erase this. This is in B, so I'll erase this. So ultimately, where does this lead us? 1 is not in B, so 1 shouldn't be subtracted, but everything else should have been. So even if you subtract this, all these things lead us nowhere, so these are unnecessary. So whatever we have, whatever was to be subtracted, we already did, and we have A minus B, as this is A minus B now, as this set. 0 is less than equal to x is less than equal to 1. So all the elements between 0 and 1, including 0 and 1, would be A difference B or A minus B. So don't panic if you don't understand this last part, this last example. You can watch it again if you want, but we will cover this example in detail in my further lecture, where I introduce something called the intervals. In my 4th chapter, I'll do it probably. So till then, I think I have covered whatever I needed to. So we looked at quite a few operations, and we also completed multiplication finally. So these are all the things you could do with sets. We'll look at a lot more examples in my next lecture, and we'll look at some other interesting way of defining sets. And thank you till then. See you.